Hello, welcome back. I hope you guys had great winter breaks. I'm sure you're really excited to be back at school. So, we are going to start out with stoichiometry this semester, and we've kind of been addressing this a little bit throughout the last couple of months. That a lot of the skills you've been learning about conversions and balancing equations and writing formulas, those skills will transfer over and we continue to be used throughout the semester. So, we are going to kind of just dive right in with a little bit of a review today. So today's going to be mainly review. Tomorrow or next class, we'll really get started on the stoichiometry part of this. But again, the stoichiometry is based around these like essential skills. So we're going to just make sure that we are still fresh with this today, and so we can move forward next class. So dimensional analysis is one of those things that you either love it or you hate it. You get it or you don't, and it's just not going to go away. So hopefully, from all of the test results I've seen and stuff, pretty much everybody's on board with dimensional analysis. But it's been a little while since we've really used it consistently. So let's go ahead and just do a little review of that. So why? Why do we need to do a dimensional analysis? Well, it's to keep track of several moving pieces. So we're going to have multiple different elements that we're keeping track of. We're keeping track of the moles. We're going to mass, to atoms, to back to moles. We're trying to figure out if I start with this much of a substance, how much will I end up with this other new substance that was formed? So there's just really a lot to keep track of in chemistry with these conversions, and dimensional analysis puts it all in one place. It's easy to cancel out your units as you go and just kind of keep track of everything. Another reason we're going to go over this today is because it's not only used in stoichiometry, but we will continue to use it in our solutions unit, and our acids and bases unit. So it's not going away. We'll just keep on going there. So at the bottom here, you guys can see this dimensional analysis setup pattern. So we're going to draw the table. You're going to start with the units you have. So whatever you're given, that value in unit will go in that first part of that table. And then you will cross over and down one. The units you have goes on bottom, and the units you're going to use to convert to get to your answer is going to go on top. So here, if you start in grams, the units you have would still be in grams. That's going to be set equal to whatever the next step is going to be for you. So if you're going from grams to moles, or anything else. So if you're converting like moles to atoms, or if you're trying to get from grams all the way to atoms, you'd have to go from grams to moles to atoms. So you kind of can have these in multi-step parts. So here you would go from the units you have. The next column over would be the units you have converted to the units that you are going to use as your conversion. The next column over would be the units that you're using to convert into the units that you want. And at this point, you can go through and you can cancel out all of those units. And then you would multiply everything across the top, multiply everything across the bottom, and then divide those to get the answer you want in the units that you desire. So an example problem here, you probably recognize these from first semester, so just kind of bringing these back. What is the mass in grams of 3.5 moles of the copper, of the element copper? So if we're starting out with 3.5 moles of copper, this is the unit that I'm starting with. This is what I have. So that means that moles of copper has to be my unit down here, because this is the units that I have. I'm going to set this equal to, I'm going to have 1 mole is equal to this many grams. Remember that we're getting this mass from the periodic table. And now I can cancel out moles. I am trying to find the mass, right? So we're in the correct units at this point, so we can go ahead and do the math to solve. So we're going to multiply these across the top, divide it by the bottom, and that gives us 222 grams of copper. Here's another one. You guys can pause this for a second if you'd like and try it. If you're not wanting to pause, then you just want to keep on going, we'll go ahead and go through it. So you're starting out with the 0.375 moles of potassium. Moles of potassium is the unit we have, so we have to put that down here. 1 mole of anything is equal to its atomic mass from your periodic table. So that's something you can remember. So if we have moles, you can always write like 1 mole and set that equal to its mass. Now, this will not always be 1 mole, and that's kind of where stoichiometry comes in and gets a little tricky. So if I'm starting out with 2 moles of potassium, I would put a 2 here, and then Obviously, if you have 2 moles of potassium, 2 moles of potassium is going to be twice as big. So as far as mass goes, so we'll talk about that as we go a little further, but it's important that you have this basic workflow down. Another example would be if you are going from grams to moles. So if I start out with 11.9 grams of aluminum, my grams of aluminum, that unit has to go on the bottom here. I know that I can go from mass to moles. We know that 1 mole is equal to the mass of that element. So this one's only different because we're going kind of opposite. So we're starting with mass, we're going to moles. So here, since we have mass on bottom, I'm just going to pull the mass from the periodic table, set it equal to 1 mole. Now I can solve this. So this would be multiplying across the top, divide by the bottom to get your moles. Another one here, if you want to pause this for a minute and try it out. But we're going to start with 5 grams of calcium. Grams of calcium has to go on bottom, so I'm going to pull this mass from the periodic table, set that equal to 1 mole, do our math to get our final answer. The next example is the third kind of way that you might see these. So if we are starting with atoms going to moles, so this one, the conversion factor you're using here is 1 mole of anything is equal to Avogadro's number. So 6.02 times 10 to the 23rd atoms is equal to 1 mole. So we've kind of just plugged in that information here. We have the units we have into our desired units here, and then you can solve that. Another one to try if you'd like to. Okay, so we start out with the atoms of lead that are given. Atoms of lead goes on bottom, set equal to 1 mole of lead. You're going to multiply, divide, and get your answer. So example problem 4, these were the longer ones we worked on last semester. This will be similar to what we're doing in stoichiometry. So they're going to be multi-part. You're going to have lots and lots of little columns in your tables, and you're just going to keep on working your way through it. So for some of these, we're going to be starting at moles, going to mass, back to moles, back to mass. So some of these are going to get pretty lengthy. So for this one, we have what is the mass of this many atoms of copper. So we're starting with atoms. So copper atoms is going to be what we have was here, what we're given. We're going to put the atoms of copper on the bottom, set that equal to 1 mole of copper. So now these atoms units would cancel out. Now I'm in my units I'm using to convert. So this would be my 1 mole of copper. 1 mole of copper has to go on the bottom here. And then we know that 1 mole of anything is equal to its atomic mass. So we're going to pull this 63.55 from the periodic table, plug that in. Now we can cancel out moles and we're in the desired unit. So we can multiply everything across the top, multiply everything across the bottom separately, and then divide them for our final answer. Okay, so another one you can try out here if you would like to. Okay, so same workflow. We're given atoms, so atoms comes down, set that equal to moles. Moles comes down, mass goes on the top, and we are going to solve that. So some example workflows. This is on here just for you to use as you're working. So if you are unsure of kind of the next step you would take for these, you can refer back to this slide. The next thing we're going to just quickly review is naming. So also naming is another thing that's just not going to go away. So we're going to be writing out our chemical formulas, putting those into chemical equations, and then balancing them, and then using that correct balance equation to do stoichiometry to figure out what our percent yield should be, what reaction efficiencies are, and that kind of thing. So this is just another one of those things that's not going to go away. So if you are still struggling with it, you really do need to figure it out because it'll be an issue for the rest of the year. So here for naming binary ionic compounds, it just means you have 2 elements, the 2 elements from the periodic table. We're not talking about anything that's a polyatomic ion or anything. So you always name the cation first, which is the metal. Okay, so the metal always goes on the left, the non-metal goes on the right. When you are naming them, meaning writing out the full name, you're going to change the ending of the second element to IDE. Okay, so here you'd have magnesium bromide, sodium sulfide, potassium phosphide. You kind of get the idea. We're ignoring the subscripts because that doesn't matter for naming ionic compounds. So if you're going to write out the ionic compounds, these are the ones you have to use the oxidation numbers first, okay? So you're going to always write the cation first, so that means the metal. The metal always goes first, the nonmetal goes second. You're going to look on your periodic table and figure out the oxidation number for those. The oxidation numbers, remember, are linked to kind of the group that they're in. So if it's in group 1, it's going to be giving up 1 electron, which means it has a positive 1 charge on it. So if you looked over where like oxygen is, that's going to be group 16. So that one's going to be gaining 2 electrons to get to 8 to satisfy its valence shell. So that one would have a charge of -2. So if that's something you need a refresher on, let me know, but that's also in our Unit 3 notes from last semester. Should be in Unit 3, I'm pretty sure. So if you need to, you can go back and check those out or just ask me or someone for help. So here we're going to figure out what your charges are, and then you're going to crisscross them, okay? So basically this is a good example here. So we have lead. In this case, we know lead counts as a transition metal. So for this example, we must have been given this charge, okay? So this charge for lead is going to be +4. And then we have oxygen has a charge of -2. I got this from the periodic table. You're going to crisscross those charges and then write the subscripts with the elements, okay? It is important to keep your subscripts up high, your charges up high as superscripts here, and then move them down as subscripts, okay? Because I am seeing a handful of people that are like really getting this confused. So, and it's because they're writing it down low everywhere, so they can't tell like if they crisscrossed it yet, or if there should be a negative or positive, or what it is. So please write your charges as superscripts up high, and then when you crisscross them, you're going to write out your subscripts down low. So this now is telling you you have 2 parts lead, 4 parts oxygen. So since this is ionic, we can simplify this. It's the same ratio here, right? So 2 to 1. So we're just going to simplify this down. You do that with ionic. You do not do that with covalent. So here are some special rule ones. We have transition metals, okay? So we know that transition metals are everything in the middle, that lower part in the middle of your periodic table. Lead and tin also follow these rules. Okay, so again, you're naming your cation first. You're going to figure out what the charge was, and then write the Roman numeral of that charge in parentheses after the cation name. Finish it up by writing the anion name and changing the ending to IDE. So here is an example of that. We have copper and chlorine. So we're going to have to figure out what this charge was on copper. Okay, so we know that cation's copper, anion is chlorine. So the way we have to do that is right here. So I'll do that again. So here we have this 2 down here with this chlorine. We're going to reverse that crisscross. And so now it's a subscript. We're going to reverse it back to the superscript, the charge, whatever those were. This is saying that the charge on the copper was a +2 before it got crisscrossed, and the charge on the chlorine was a -1. We're going to double check that part on the periodic table and just make sure that that chlorine really is a -1, that this isn't a simplified version of something. It's not in this case, okay? So chlorine is -1. So that means that this charge on the copper had to have actually been a +2. So we're going to write it out. So copper, parentheses, 2, because that's the charge on the copper, and then chloride, changing that ending to IDE. Writing your ionic formulas for transition metals is actually a little bit easier. So your Roman numeral is going to tell you what the charge is, okay? So that's one less thing you have to look up. So here we have this example, tin, 2, chloride. This 2 tells us that this tin has a charge of +2. So that part's done for you. This chlorine, we're going to look up and see that it's in group 17, so it's going to have an oxidation number of -1. Now we can crisscross those 2 to figure out what the subscript should be. So this 2 is going to come down here with the chlorine. The 1 would go with the tin, and we would write it out like this. Remember, we're not writing 1s in formulas, just anything 2 and above. So here we have this. So again, just a reminder that this is ionic because you have a metal and a nonmetal. So since it's ionic, there are no prefixes. Naming compounds with polyatomic ions in them. It's kind of a special case with these. even if everything in a polyatomic ion is a nonmetal, it still behaves as an ionic bond as far as naming goes. Okay, so whenever you have these, like if I had like CHO here, yes, those would be 3 nonmetals, but they still, the naming still gets applied from the ionic rules. Okay, so if you have a polyatomic ion, here you're going to still kind of the same idea. You're just going to name the first. Okay, so we're going to name the first part of this, which is the metal. So it's going to be sodium. And then we're going to look up the rest of this here for the polyatomic ion, which this one happens to be permanganate. This one, there's some notes here about like some special cases here with permanganate. Permanganate changes its name based off of its charge. So that's one you'd have to kind of keep an eye out for, but we won't come across it very often. If this charge was a -2, it would change it to manganate instead of permanganate. But like I said, most of the time you are just looking at this polyatomic ion, looking it up on your chart, it gives you the charge and you're good to go. So here you'd name your first metal, whatever is first is going to be your metal, with the exception of ammonium or ammonia. So that would be NH3 or NH4. That's an exception. But the rest of these will be just your metal first and then your polyatomic ion. So you'd be finding that on your sheet with polyatomic ions on it. So here, if you are writing your formulas for polyatomic ions, it's the same rules as the binary ionic compounds. So we're going to find the oxidation numbers for these and then crisscross them. So calcium has a +2 charge because it's in the second group. Nitrate, we're going to look at this up on our sheet. It's NO3 and the charge is -1. The NO3 is like a little unit. It's like a little packet of information. This cannot be changed. It cannot be reduced. You cannot add anything to it directly. It has to be in parentheses. Okay, so you want to kind of think of this as like its own little thing, and then the charge is what you're worried about here. So we have a +2 and a -1. So we're going to crisscross those. Okay, so this 2 came over on the outside of this nitrate. Again, this is in parentheses because this 2 applies to the entire ion, right? So it's gonna apply to the nitrate, not just the oxygen. So we're gonna put this in parentheses, the 2 on the outside. This 1 from the nitrate would cross over here, and this is what you would end up with. Okay, so oops. Here's some examples. I'm going to stop this real quick. If you need more examples, I have gone through and done a ton of them on the board. Okay, so I've walked you guys through like one of every single kind of example so that you guys can see it. So if you guys need a little more help with this, you can go back in the slides and refer back to this video. So naming your covalent compounds, these are easier, okay? So we are just using your prefixes to show that how many there are. Again, covalent is 2 nonmetals, okay? So 2 nonmetals. The nonmetals are in the upper right-hand corner of your periodic table. It's a very kind of small, it's a limited amount of elements to choose from. So you're going to use 2 prefixes. You can use a prefix on the first word and the second word, and then you change the ending to IDE. The only time you will not use a prefix is if the first element is just 1. You would never say mono on the first word. Okay, so mono only applies to the second word. But beyond that, you can put these prefixes on both words, and the subscript will tell you which prefix to use. Okay, so for naming them, see, so here, in this case, you'd have your first element is silicon. There's no subscript, so that indicates there's only 1 atom. So since that's a 1, we're not putting mono on the first word. This is just going to be silicon. And then we look here, we have fluorine. There's a 4 after it, so that says that there's 4 atoms. So we're just going to write out tetrafluoride. So again, we're changing the IDE. What's important here is we are not crisscrossing these. Okay, you do not crisscross covalent with covalent naming or formula writing. Okay, so that crisscrossing is only an ionic thing, because crisscrossing in ionic is a way to balance out the charges that are being lost or transferred. In covalent, they're sharing, so there's nothing to crisscross, right? So they're sharing electrons. Neither one of them is losing or gaining anything, so there's nothing to move around. There's nothing to change or transfer. So just make sure that we are keeping that in mind. Okay, so a couple examples of this. Again, we're just naming the first one, naming the second one, adding in these prefixes where needed, changing the ending IDE on the last word. So we have like dinitrogen pentoxide, dihydrogen monoxide, and so on. Okay, so writing your covalent formulas, these again, also easy. So the prefix tells you what the subscript will be for that element, and that's all you have to do. Okay, so phosphorus is going to be di, so di stands for 2, so we would write P2. Pent or penta is 5. We know that this is oxygen, so we're going to write O5. Again, no crisscrossing because it's covalent. They're sharing all of this. They're sharing all of their electrons, so there's no crisscrossing going on. Okay, a couple more examples here. Just kind of pay attention here. You have tetra, which is 4, deca is 10, so we would just put those in as our subscripts. Very last thing I kind of want to go over here is balancing your chemical equations. Okay, so again, we're not losing this skill. We're going to keep on using this. So you're going to have to continue naming your formulas, writing them out as chemical equations, and then balancing them before we can do any kind of math. Okay, so this unit especially is kind of lengthy. Not the unit itself, but the work is. Okay, so it's something that some people just really love it because it's a process and you're going to come out with a definite answer. Everything kind of clicks and works and comes together. Some people hate it because it might take up a whole sheet of paper to do one problem. So either way, it's this unit that we're going to get through. We'll kind of use these skills throughout, but you guys will be really good at it by the end of it, hopefully. So with our chemical equations, just remember that these are representing the identities and the amounts of the reactants and products in a chemical reaction. That's important. Okay, so the coefficients you guys add in to balance these equations are going to directly affect the math that you're going to do with that. So if you look at the bottom here on the reactant side, I have 1 mole of copper on the reactants, and then if I switch over, let's say I have 2 moles of silver on the products. That's going to make a big difference because you're using that amount of moles in your dimensional analysis to determine like how much you're going to produce of something. So if you get the balancing wrong, the whole problem is going to be wrong. So it's really important to kind of have this down. So remember that we have our diatomic molecules. These are going to always be in pairs. So have no fear of ice cold beverages. That's a good way to remember it. If you have another way, that's great, but that's the way I was taught in college, so that's the way I'm going to show you. So have no fear of ice cold beverages. Keep in mind that the C stands for chlorine, not carbon, and the BR stands for bromine, not boron. Okay, so that's important. So we have chlorine and bromine for those 2 letters, part of that. So again, just kind of throwing this up here in case you want to review it. If you come across an equation you're not really sure what a symbol means, you can refer back to this. So just keep in mind that you will sometimes, actually pretty often, see the states of matter or the phases of matter listed, kind of to show you just kind of what phase it was in during the reaction. You will also see things like on the bottom half here where if a certain amount of heat was needed, like if we've added a flame or if it needed to occur under pressure or a certain temperature, if you needed to add a catalyst, all that information is going to be given to you in your chemical equation. So here again is how you would differentiate what your states of matter are, kind of a reference piece again if you need to come back to it. So with balancing equations, you guys are adding in the coefficients in front of each molecule or bond, I guess I should say. So you're going to add these in as needed to balance them out on either side. Okay, so you want an equal amount of each type of element on either side of your yield arrow. Okay, so here we have 2 nitrogens on this side. You only had 1, so we added a 2 in front of this to multiply this to make this 2 nitrogens. That's great. Now we have 6 hydrogens. That's why we added in the 3 here to make it 6 hydrogens on that side as well. Okay, so kind of some guidelines. You want to keep track of your elements as you work. T-chart works really well for this. So what you're doing with the T-chart down here is just kind of keeping track of how many you have on each side. You don't have to write in that you're multiplying it by 2 and that's going to equal 2. You can just scratch out this one and say, okay, now I have 2. Okay, what you are writing in front of these molecules is the number that you're multiplying them by to equal what's in the T-chart. Okay, always check if you're adding something in, you're always checking to see what else has changed. Always start with your lone elements in metals and then do hydrogen and oxygen last. So most of the time, if you start with your metals or elements that are by themselves, you'll end up balancing hydrogen and oxygen kind of inherently. So leave those until last. And oftentimes, like hydrogen and oxygen show up in multiple places, which makes it a little more complicated. So don't start there. Start with the metals, and the rest will probably work itself out. So with this example here, we've got one zinc on each side, one chlorine, then two chlorines on the product side, one chlorine reactant, two hydrogen products. So here, zinc is going to be my metal. Well, that's where I would start, and it's already balanced. So the next thing I'm going to do is the next best thing is going to be chlorine, because I'm going to leave hydrogen until the end. So for chlorine, I'm going to have to add a 2 in front of this hydrochloric acid to balance my chlorines out. Okay, so those are done. That's great. But what else did it change? It also changed the hydrogen. So now I have 2 hydrogens as well. Oh, looky there. It balanced everything out. Okay, so that's what I mean about starting with anything except for hydrogen and oxygen. Here's another one. It's a little bit more lengthy. So I've started this out. I have the reactant side, the product side, and all of the amounts listed out for you already. We're going to start with aluminum. So we're going to add in a 4 here in front of this aluminum hydroxide to balance those out. So we changed aluminum, but we also changed oxygen and hydrogen. Note that hydrogen pops up in more than one place, so make sure you're adding them all up to get that correct number on the product side. So then we're going to go in and balance the carbons. Okay, so we're going to add a 3 there. Again, changes the hydrogens. And then we can come in and add a 12 in front of this one to balance out the hydrogen and oxygen. Okay, so that is it for today. Just a lot of review. I know this stuff will come right back to you guys. So if you are really having any trouble with it, please let me know. It's very important that you do understand this and you have a fairly good foundation of it before we move forward. So today's practice is just going to be over these things. Again, you'll have a couple of conversions, dimensional analysis, some naming, and then balancing. And then we will get into the nitty-gritty of stoichiometry next class. So get your practice questions done. Let me know if you have any problems, and I will talk to you guys next time.